Assalamu alaikum. Good morning. Last time we discovered some basic elements of linear algebra that we will be using now for quantum mechanics. Okay, so let me quickly remind you of what we are going to do now. So we have Hilbert spaces now. So it's a vector space with an inner product. We have for n-dimensional Hilbert space, we have n linearly independent set of vectors that we will be using for basis. We will be using orthonormal basis actually. So and last time what we saw is how we can represent a vector in this Hilbert space in terms of these bases. So for example, let's say we have a vector v, and let's call these vectors phi n, where n goes from 1 to n. So let's call this capital N. Then we can expand this in terms of those. So it's like 1 to n and some coefficients that we can use the same label here as n maybe, and then phi n, where this number is simply this vector projected onto this basis vector. So this is what we saw last time, and what we are going to do now is we are going to represent operators in this space in terms of these basis vectors, and it's very simple. So let me start from here. So let's take an operator A in this Hilbert space. Then what we can do is, if this is our basis, then the easiest thing is we can write identity operator in this space in terms of these. Like this. Now this relation, this linear combination of these bases can be formed using this identity by just projecting this V onto this. Similarly, we can do that with an operator. So let's write this equation or identity, and then we multiply one here and one here. By definition, it's still the same operator. And now on this side, let's call this this index n, and it runs from 1 to capital N. So I'm not going to write that. And just like that. And on this side, let's use another label for this dummy index, and let's call that M. Now what you can see is we can take this sum outside. This will be a double sum, and this, and this. So this is an operator. This this is an operator, so this operates on this, gives a state, and this is an operator that makes that state a number, just like an inner product. So we have phi n, and then that number phi m, and we can remove extra lines if we want, but I think we don't need that here, like that. So this is a number. Again, this is an operator. Because this is an operator, it has to be an operator, so that operator nature is here. It projects this to that. This is just a number. We can call this A N M, and what this A N M is, actually it's matrix element of this operator in these bases. So this is a matrix element of this operator in these bases. So this is A N M. So it's nth row M column, as usual for matrices. So now we can take this number here. So this is how we represent an operator in certain bases. So what we need is these numbers. Okay, that's one thing. Now one thing that we left last time is define the adjoint or Hermitian adjoint operator for A that Parvez later did. So I'll make that a little easier, I guess, because there are people who can't maybe think in two steps. So maybe we can remove this as well. So let's suppose this is an operator in a Hilbert space, and we can define its adjoint, and in general it can be a different operator. So let's call it B, and B is defined as adjoint of A. So here when we put this symbol here, it means adjoint of this operator, and in general it can be different, so at the moment we are using this label. Okay, so it's B. Now the way we define this B, so we take any arbitrary set of pair of states in the same Hilbert space. So let's call them phi and psi. So they can be any two vectors in the Hilbert space. So if what we can do is, if this number is equal to this number for any arbitrary vectors in the Hilbert space, then this B is by definition adjoint of A. So this is just a symbol, but here it's actual definition. So once you write that symbol here, it becomes what last time Parvez explained. So it's basically this thing. So this is how we usually write. So it's in general another operator. We use the same label A, but we put a dagger here. So if this equation is satisfied for any two vectors, then this is adjoint of A. Okay, so that's the definition, but I thought maybe if we use another symbol and go through in two steps, that would be easier for many people. Okay, so that's the definition. Now for Hermitian operators, we discussed last time that a dagger is equal to A, and its consequences, its eigenvalues are real, its eigenvectors make linearly independent set, basis set basically, and we can orthonormalize them if they are not already, so can be chosen as basis. So we can use plural for basis. So that means that if eigenvectors of A are say alpha with eigenvalue, let me use this symbol, A alpha, then these alpha will make a complete set. That means we can write resolution of identity in terms of these. Like that. So for quantum mechanics, we will have Hermitian operators, and we will be using their set of eigenstates as basis quite frequently, especially for Hamiltonian operators. Okay. So now we can use this with this. So let's say we use these bases for the same operator. That's, we are using eigen bases, that's what we call. So eigenstate of an operator to represent itself. So we can represent an operator in any basis. It looks like this. So it becomes a matrix. In general, all these elements are non-zero. But what happens if we choose these bases that are eigenbases, that are eigenstates of this? That means in this case we choose alpha as basis. So that becomes quite interesting. So we can start from here maybe. We can simply compute this one. Yeah, that's easier. So instead of phi and phi m, let's call them alpha and beta. So these are just labels. So we usually sometimes what we do is we write a state, for example this state. Sometimes we write it as this. It depends on convenience, and sometimes we may use psi, this symbol, sometimes lambda, sometimes alpha, beta, gamma, delta. So it doesn't matter. So all what matters is that we choose some symbol as usual to represent certain object and consistently use the same symbol. So okay, so this is just a symbol to represent that state. So I mean, there are different ways to write that. It doesn't actually matter. So all it matters is that we know which state we are talking about. So here that's the index n. It runs from 1 to capital N. Then we can distinguish that these are different phis, phi 1, phi 2, etc. But we can simply use this label 1, 2, 3. That carries the same information. So doesn't matter how we name it. Okay, so there's nothing mysterious about these symbols. It's just a label. Okay, so this is in this case. So what happens for this? So if we use alpha and beta, that would mean that a operator will be like alpha beta, and alpha beta will be again like n and m. So like that. So if we choose this, that these states are eigenstates of this, then this matrix element now we can operate this on that and simplify this expression. So it's like alpha. If these states are eigenstates of this, then we will get beta again, but with some number, and similar to this we will call it a beta. Okay, so it's like a beta and beta. Now this a beta is just a number, we can take it out of this inner product. It doesn't matter if we multiply it here, here or in here. Okay, if we multiply it here, we might need to have its complex conjugate, but if these operators are real, then these are real, operator are Hermitian, then these numbers are real, then we can even multiply it here inside alpha, okay, inside the dual. So what we get now is a beta alpha beta. Now what would be this inner product? So if we say that our bases are orthonormal, that means every vector is perpendicular to every other vector and they are normalized. So that means that this quantity so this is basically just writing expression, a mathematical expression for orthonormality. So this means that it's either 0 if alpha is not equal to beta, or 1 if alpha is equal to beta. Okay, and instead of writing these two statements, we have a shorthand. So we write it delta alpha beta. So this is a delta symbol and we put in the subscripts alpha and beta, and this is called Dirac delta, Kronecker delta. Okay, so it actually means this. So it's 1 when these two indices are same, it's 0 when these indices are different. Okay, so now we can simplify this expression. Here, and we can put it here, alpha beta. Now if there were a sum here over alpha or beta, then there would be a huge simplification due to this delta function, because it's 0 for most of the time, and that sum is here actually. So we can now put this alpha beta into this expression, and so operator A now this is A beta, delta alpha beta. Now since this function is only 1 or non-zero for when indices are the same, so this double sum is reduced to single sum. Okay, so whenever alpha is not equal to beta, it becomes 0, so there is no contribution in the double sum for that. So it's like if you have these two sets of values, so double sum would be like counting everything, and this delta function will mean that you are going along diagonal when these two are equal. Okay, so now it becomes just a single sum, so you discard everything over here and here, you just go along this, so it's a single sum. So let's call that alpha, and if this is alpha, then this also becomes A alpha, okay, because now when it's non-zero, alpha and beta are equal, so we can name them anyway we like. So this and this beta also becomes alpha, okay. So sum is reduced to 1, delta is gone, and this beta becomes alpha everywhere. We can make alpha equal to beta as well, but since alpha and beta from compared to beta, alpha is simpler maybe because it comes first, so we usually use alpha, so it doesn't matter much. But so this, now look at this. It looks quite like a resolution of identity when you just look at this thing, but in resolution of identity there is always 1 here, but here there can be some other number. So the simplification by using these eigenbases is that these two are the same. And what does that mean in terms of a matrix? So in terms of a matrix, now you see that there is only one index here. So instead of A and M, we only have A alpha, and this is alpha alpha. So in terms of matrix, we only have diagonal elements, okay. So that's already clear from here. So representation of A operator in its eigenbases will be diagonal, and it will be like A1, A2 and so on. So everything else is 0. Okay, now this representation where you resolve an operator in terms of its eigenbases, it has another name as well. So it's like it's called usually spectral theorem, okay. So you can resolve a Hermitian operator in its eigenbases and write this expression where these are eigenvalues. So now you see, if we write an operator in an arbitrary basis set, then it's a full matrix. Arbitrary basis, okay, and eigenbasis. It is diagonal. Now we can go from here to here by using transformation actually, and we can use similar transformations to change basis of a vector or an operator. So now let's talk about that. So this is one example, but this is very special example, but now let's take a general case. So how to transform basis? That's how to transform representation of an operator by changing its basis. So suppose these are these alpha, we can call them a set, basis set. So these are one basis that we are given, and we know matrix elements here, and we want to choose another basis, and let's call that basis mu. So we will be using mu nu. Now in this case, we don't assume that these are eigenbases, okay. So this can be any general basis. So we can use nm as well, but it's already written, so yeah. Or maybe I should use nm, I guess, because it looks simpler. but I'm not going to write phi n, I'm going to write nn. So now the other basis can be alpha, beta, or mu, nu. Okay. So how to change this basis? That's the question. So what we can use it, we can use resolution of identity in terms of these bases here. So it's like so this is resolution of identity in this basis. If these bases form a complete set, then this is a valid expression. We can put it here and here. Okay, so we will get this thing. Another, in terms of nu, we need to use a different index here. Now, similar to what we have done earlier, this is an inner product, this is an inner product. And what else? So we have an m, mu, nu. We have 4 indices now, and we have this a and m, and we can expand that a and m. Okay, so it becomes easier. So we have now mu n 1, then m nu, another number, and then we have mu nu, an operator projector, and then a and m. So let's write that a and m like this. So now what can you do about this? So this is a number, this is a number, this is a number, this is an operator. But you see certain pattern here. So nu n, m mu, n m. If we write this in the middle, then it would become nu n, n m, m nu. So let's do that. Now, if you are just doing mathematics and flowing, then you can find another simplification, that you can use this with this sum as one, this with this sum as another one. Okay, and then you'll get another expression with mu a nu and then this. Okay, that's actually what we are after. But here we suppose that we are given this number or these number or this full matrix, and we want to use this. Okay, so we want to use NAM. We can't just change it to something else that we can't use. So the other thing, mu a nu, that's equal to, that's what we are after actually. You can call that mu new. So this is matrix element of this operator in these new bases. That's what we are after, and this is what we have got. So if we know this, how can we go here from here to here? So actually we would need this and this as well. So if we know this and this, and this is similar to this, so they have the same information. So if we know these two objects, then we can calculate this. So what you can do is, first we can write is mu new, and then this sum over here, and m, and let me write this as an m now, and this is n mu, and then mu new. So that clearly means that this thing is a mu new, this in this bracket. Now what are these objects? These are inner products between old basis states and new basis states. So these inner product carries the information that how our old bases are related to the new bases. So these are kind of expansion coefficients for this mu in terms of n. Okay, so let me what is this? So it's like if we have this state and we like to expand it in these old bases, then this will be new nth element of this mu. So it's like expansion coefficient. Sorry, no, it's the opposite. So it's let's take the other element, this one. So we have new and we have n, maybe that's m, yes. So this is expansion of a representation of this new basis, one of the new basis vector in terms of one of these old bases. So there is some over here. So this is like new m. So this is a number, it's new m. We can call that new m. Okay. So it's new basis vector in terms of old. So I'm writing this because this statement is very important to remember this. Okay, so the information we need to transform the basis is this one. So we have to know new basis in terms of old basis. If we know this, then we can transform the basis for any operator. Otherwise, we don't know how the bases are related, so I mean, we can't do that. And instead of writing this as a single vector, here we have sum over mu and nu. So what we can do is we can write, we can make a matrix out of this for all bases. So instead of one new m new, let's use this symbol u for the whole set of new bases written in terms of old bases. So it's like new 1 in terms of old basis, so that's one vector. So it's like Okay, so this is also, so it's like a new mu. So suppose this is new, so I'm just writing it here outside this matrix. So this is new 1, new 2, and so on, new n, then mu 1, mu 2, and so on, new mu delta, etc. Whatever label are we using for these new mu bases. So they will become column vectors in a bigger matrix. So if we do this, then it becomes very simple. How? Then this object is simply, where should I write? This object is simply um new. Okay, so because this new is for the column and n is for the row, so new runs over here, m runs over here, so it's row index, column index. So this is the first index, this is the second index. So this whole thing, when you vary these two, is a matrix basically. So there are two indices, so it's a matrix. Okay, so we call that new. Now what about this? If this is mu new, then this would be like u maybe dagger, and for u dagger it's mu n, because in general these are complex vector spaces, so it's not simply transpose. So if you change, then this is not simply a transpose. This inner product is for this complex vector space. So this will be mu nth matrix element of u dagger. Okay, so this is matrix element nth matrix element of another number. So now if we write this expression in terms of these matrices, so let me just write this expression in the brackets, sum over nm, and then mu dagger mu n a and m u m new. Now let me first tell you, if you multiply two matrices using simple matrix multiplication rules, then this is the form that you get. Suppose if you have two matrices A and B, and you want to multiply them, so you want to calculate A, B, we can call it C. Then the way to do that is that matrix element of this C, suppose an mth matrix element of this C, that means nth matrix element of this product AB. So this is just how to write that. It will be equal to sum over another index, let's call that P. P goes from 1 to n again, and it will be equal to n p p m. Okay, so this is the structure. So this common number here, that's we sum over that dimension, and this is free index here. These are dummy now, so we can use any label for that as well. So these two are free, so they come over here. So where
here ये जो sum है P
नहीं, इसमें कोई आइडेंटिटी का कोई रोल नहीं. So it's just a matrix multiplication. So you can test this on say 3 by 3 matrices. Okay, so that's an exercise that you can do. Okay,
because it is similar to insert an identity here.
I don't know, maybe, but we are not doing anything with identity now. We are just using matrix multiplication. So the basic rules for matrix multiplication that we usually learn in linear algebra for simple matrices, that gives this kind of product. So that's the matrix product with another matrix. Okay, so matrix multiplication. So that's the rule basically for matrix multiplication. So for two matrices, we don't multiply them element by element. We use this rule. Okay, so that's the rule. But what I want to highlight is the structure. So if they are written in terms of this, in terms of products of their matrix elements, then this is the structure, that there will be free indices on the outside, and there will be dummy indices where we are going to sum in the inside here. So they are yeah, so they are inside. So it's like NPPM. So these two will be closer. Okay, there is nothing in between these two indices. So so this is the structure. Now we can generalize this for 3 matrices, 4 matrices, etc. And if there are 3 matrices, then there will be another, suppose there is a D matrix, then what happens is that A, B, D, and nth element of A, B, D. Suppose their dimensions are consistent, number of rows and number of columns. Okay, so they are consistent, so that we can multiply them. And in this case, our operators are always square matrices, so that's no problem anyway. But A, B, and D and M. So an nth element of this product, the rule is, now we have two sums, P and Q, so it will be N over here and M over here, and we can use P or Q. Suppose we use P, Q, then P will be here and Q will be here. So it's like PP, QQ, and then these are the free indices on the outside, and you sum over all these. Okay, so that's the rule. Now if you know this form, then you can identify what this thing is. So there are two sums, there is mu, there is an n, there is mm, and then there is this nu, and sum is over n and m. So these two are dummy numbers and they are in the same order as this. So this is basically a matrix product for 3 matrices. So it's like U dagger, A, U, and it's mu, nu. Okay. So if mu nth element of A is equal to some things and then mu nth element of that, that means the whole matrix is equal to this. So A in terms of new basis, so since in new basis the numbers are different in general, let's put a hat, a tilde, or something. No, hat is for operators here, so a tilde here, just to distinguish that it becomes a different matrix in new basis. So maybe we use the same here. So this is now U dagger A U. Okay, so what this tells us that if we have an operator in one basis, and if we know some other basis in terms of the same basis that we already have this matrix in, we can do this transformation, this matrix multiplication, and get our operator in new basis. So this is transformation of basis basically for this operator. So it's basis transformation. Okay, so this is very important because in for quantum mechanics we usually need to change basis a lot. Okay, you will see that in today's lecture. So any questions about the, yes?
I had a question about the canonical delta. You said that like canonical delta assumes that the two vectors are perpendicular, right? So do we always assume that they're perpendicular, or like we're given that they're perpendicular?
For this case, we are assuming they are perpendicular, they are orthonormal bases. Yes.
So what if they're not perpendicular? Do we
Then it will not be a delta, there will be another overlap function. Yeah, we usually call that S, but that makes things a little complicated, so it's simpler to use orthonormal basis. Yeah. Any other question about basis transformation or spectral theorem? Okay. Now maybe one more thing before we actually start quantum mechanics. And since now all operators can be written in terms of whatever basis and in terms of matrices, now things will be very parallel to matrices. So linear algebra basically in terms of matrices, things we do in terms of matrices. So operators will be matrices usually in some basis, and so we will assume we are working with Hermitian operators, okay, for quantum mechanics problem. So we don't need to consider other non-Hermitian operators. So what happens? So if so since we know they are similar to matrices, they can be represented as matrices. So for matrices we know that for two matrices A and B, AB, the product AB is usually not equal to BA, okay, for matrices. Now the same thing is true of course for operators. If you represent them as matrices, then AB will not be equal to BA, and this is called that this product is non-commutative, okay, and we can use another symbol to represent their difference. So if they are not equal, there must be some non-zero difference, okay. So AB minus BA. So let's call this quantity this thing. Okay, so that's just a symbol to represent this quantity. So we call this commutator. So this is a commutator between A and B. So now the question is, what happens if this commutator is 0? That means if this is commutative for two operators, and what happens if it's not? So this has very profound consequences for quantum mechanics problems. So let's suppose A and B, they commute. That means AB is equal to BA. That means their order doesn't matter. You can change their order if they are applying on certain vector. Now I'm just stating the result. You can see proofs in maybe Griffith or Lebov or Shankar, yeah, maybe just Google it, okay, but it's very simple. So that's an exercise, okay. So what happens if they commute? So we have a Hilbert space, we have two operators in that Hilbert space, and we are going to see what happens if they commute. So if they commute, the good thing is that they'll have a set of shared eigenstates. So in general, eigenstates of one operator are different than eigenstates set of eigenstates of another operator. But good thing is, if they commute, they share their eigenstates. Okay, so consequences is shared eigenstates. So let's say lambda is eigenstate of A. So we will be using A in the form of operator and sometimes as matrices, so it doesn't matter. So maybe even in operator form we don't put hat there, so it's quite obvious what we are talking about. Okay, so we operate A on lambda and suppose it's an eigenstate and its eigenvalue is A lambda. Then if B is another operator in the same Hilbert space and it commutes with A, then if we operate B on lambda, we will also get the same lambda again, but maybe a different eigenvalue. So let's call that B lambda. Okay, so they have shared set of eigenstates. That's one thing. There are slight complications if there is degeneracy, but yes, I'll explain that in a moment. So first, brief overview. So if two operators commute, they have set of shared eigenstates. Their eigenvalues, of course, belong to them, so they are different. Yeah. Now, if they don't commute, then of course we don't have shared set of eigenstates. So at the moment, let leave it there. Yeah. Now, when they do have shared eigenstates, then usually when I was talking about spaces, then I told you degenerate subspaces and degeneracy. So suppose A has a degenerate subspace. That means that there are some vectors lambda and lambda 1 and lambda 2 that have the same eigenvalue for operator A. Okay, so A operator on lambda 1 is equal to, let's call that A lambda 1 and if we operate it on lambda 2, this is the situation that we often see in quantum mechanics. And this A lambda 1 is equal to lambda 2, that is, they are degenerate. In general, there can be more than two, but let's assume there are just two states that are degenerate. Now, the slight complication that can arise in that statement is that if there are two states that share the same eigenvalue, they are degenerate, then if we make a linear superposition out of these two, then that superposition will also be an eigenstate of this with the same eigenvalue. Okay, and that's what causes some complications. So let's call it lambda tilde. Yeah, so this is a specific linear combination. So C1 times lambda 1 plus C2 times lambda 2. So we can use these as basis. So suppose these are orthogonal and it's easy to write this. So these are projection of our proposed state onto these two, DC1 and C2. Okay, so this is a linear combination. We can expand, or we can basically create or build another state out of these two. And these two are degenerate. So if we apply A on lambda tilde, we get C1 time A lambda 1. A lambda 1 and A lambda 2 are equal, so I'll be using lambda 1 just. So okay, so these two are equal. So since these two are equal, we can make we can take that them as common number here, and then this is C1 lambda 1 plus C2 lambda 2. Now this C1 lambda 1 plus C2 lambda 2 is again lambda tilde. So that means this linear combination is also an eigenvector of A with the same eigenvalue. And now we haven't fixed this C1 and C2. It's not for a specific combination. It's for any arbitrary combination of these two. So as long as you are within this degenerate subspace, you are making a superposition of degenerate states, your resultant state will also be an eigenstate. So in the degenerate subspaces, you can make any linear combination and that would be an eigenstate. Okay. So now this makes things complicated for this. So these two vectors are degenerate for this operator. Their eigenvalues for this operator A is the same for the two vectors, but it doesn't have to be the same B lambda 1 is equal to B lambda 2 for the B operator. So even if it's degenerate for one operator, it doesn't have to be degenerate for the other operator. Yeah. So if that's the case, then this linear superposition will not be an eigenstate of this B. Even if lambda 1 and lambda 2 are eigenstates of this B, an arbitrary linear superposition will not be an eigenstate of this operator, because then you will have for B, let's suppose we apply B here, then there will be B lambda 1 and B lambda 2. So there will be B lambda 2 here. So we can't take B lambda 1 or B lambda 2 out. So it's not proportional to lambda. These are two different numbers, so unless they are the same and you could take them out, you can't get this. So this superposition is not an eigenstate for that. But the good thing is that you don't have to choose this lambda or another lambda. Even if you are given with this lambda and another lambda prime tilde, two vectors for this two-dimensional subspace. So these two would make a two-dimensional subspace. Okay. So if you are given any arbitrary orthogonal vectors or whatever vectors, linearly independent at least, vectors in this degenerate subspace, two-dimensional degenerate subspace, you can always make the right combination. That's suppose this is the right combination. Then you can always form from them these lambda 2. Okay. So you need to fix the orientation in that degenerate subspace of one operator so that it can become the eigenstates of another operator. Okay. So it's always possible. Huh. You just need to rotate them in that degenerate subspaces. That's our unitary transformation. It depends. I mean, you need to know what the eigenstates of B are. Otherwise, I mean, you can't make this special combination. So if you make that special combination for B, then it will still be it will still satisfy this equation for A. So for A, it doesn't matter which orientation you choose, but it matters for B. So you choose the right for B. Yeah. So you need to know this. I mean, there is no magic here. So you need to know this, and it's for I mean, once unless you know this, you can't make that. Yeah. Okay. So now we know about the basis transformation and commutators and their consequences. What if they have shared eigenstates and no eigenstates? Now let's move to quantum mechanics, and I'll talk about basic axioms or postulates of quantum mechanics, and then this difference will make some sense. So first thing, so there are few postulates that we actually use as principles. We rely on them for quantum mechanics, but we still call them axioms or postulates somehow. Anyway, so first is that quantum mechanics, the purpose of quantum mechanics is to study the real world, okay? And for real world, we know the physical quantities are real. That means the operators corresponding to those, if we want to use operators, then should be Hermitian. So this is a postulate for quantum mechanics. So observables are represented as operators. So every quantum system has its Hilbert space, and these are operators acting on that Hilbert space. Okay. So they are operators, and yeah, that's one postulate. Then in physical world, what we do to know about some system, we usually do some experiments with it, and in those experiments what we usually do is we measure things. So the postulate is that how to measure. So what it means. The postulate is that if we measure a physical quantity, the only outcomes that we can obtain are from the spectrum of the corresponding operator. Suppose if we like to measure energy, then the only possibilities that we can get are from the spectrum of energy operator, Hamiltonian. Okay. If we want to measure momentum, again the only possibilities are spectrum of the momentum. Okay, and the spectrum here means eigenvalues and eigenfunctions. So eigenvalues, let's focus on eigenvalues. So the only outcomes of a measurement are eigenvalues of the corresponding operator. So every physical quantity has its operator, we call them observables, and these are operators, and every operator is Hermitian, and it has its eigenvalues and eigenvectors. So whenever we measure that thing, we are going to get some eigenvalue. So measurement will give us eigenvalues. So one measurement will give us one eigenvalue. Okay, it's probabilistic. So just like throwing a coin has two faces, head and tail. So if we throw it, we get either head or tail. For a fair coin, it's 50-50 probability, but we don't know which side we are going to get. In quantum mechanics, the probabilities for different outcomes are not 50-50, depends on the state the system is in, but there are still multiple probabilities usually. Okay? And whenever we measure, whenever we make a measurement of an observable, we get one of the outcomes, but it's probabilistic. We don't know which one we are going to get. Unless there is only one possibility, then it will be certain and that it will be special case. But if there are multiple possibilities, if the system is in a state, so that's another postulate actually. So let me put that here. So the system has a state, a quantum state in the Hilbert space. Okay, it is represented by that state, and measurements will be related to that state actually. Measurement of any observable will depend which state the system is in. So it's just like classical particle. If it's moving with a given velocity, for example, and you measure its momentum or velocity, you get some value. So its state is represented by its coordinates and velocity. Yeah. So similarly, a quantum system is also represented by a state, and that state is a vector in the Hilbert space. So we usually call it state vector. If we project it onto coordinate position space, then it becomes a continuous function. We call it a state function or wave function. Okay, so that's the terminology, but let's keep things simple. So system has a state, it's in the Hilbert space. Okay, whenever we measure some physical quantity or observable, we get some of its one of its eigenvalue probabilistically. So we don't know exactly which one, but there is a probability for each. And state. So state is a vector in Hilbert space. Its own system has its own Hilbert space. So okay.
So,
Yeah.
can you first postulate that there is a state that can be used for position of different states, and then the measurement of it would give you just one eigenvalue?
I'll talk about everything. Don't worry. Yeah, these are important, so I'll not skip them. Yeah. So, what quantum mechanics postulates is that physical quantities are observables. These we call them observables. These are operators in the Hilbert space. The system is represented by a state at any time. System is represented by a state, and that's a vector in the Hilbert space. Okay. So physical quantities are operators in the Hilbert space. State of the system is a vector in the Hilbert space. Okay. Whenever we measure something, we get one of its eigenvalues, probabilistic.
Not physical quantities. Observables are.
Yeah,
physical
yeah,
quantities.
observables.
So I think slightly misspoke.
No.
Operators are not physical quantities.
No, for observables we have operators. Yeah. So for physical
Each
quantities,
observable there corresponds.
yeah, Hermitian operator. Yeah.
So if it's a momentum, which is an observable, there's a momentum
Yes.
operator.
Yes.
Position operator.
Yes.
Etc.
Yeah. So it goes from here to here. So every observable has an operator, a Hermitian operator. Yeah. So not every operator is an observable. Yeah. Okay. So now about this point, about the measurement. So as I said, there is a probability to get any eigenvalue. But what are those probabilities? Of course, that should depend on the state of the system. Okay. So state of the system, let's call it psi. And now this state can be expanded as a linear combination in any complete basis set. Okay. So what we are going to do? So we are going to relate outcome of this measurement with this state. So for a given state, what would be the outcome? So we know that there would it will be an eigenvalue, but what are those probabilities? And that's very important. To do that, what we need is, we need, suppose we like to measure, there is an observable A, an operator A for that, yeah. So we like to measure that quantity A, okay, observable corresponding to A. And what we are going to do now, this state of this system could be any vector in the Hilbert space, but we can expand this in linear combination or as a superposition or in basis of eigenstates of this operator. So that's what's needed to compute those probabilities. Okay, so whenever we perform a measurement, we are going to obtain some eigenvalue a n, but what's the probabilities for those n? That's the question. So n can be 1 to n. We like to know this thing, these probabilities, and that can be easily done if we expand this in basis of this. So for these eigenvalues, there are corresponding eigenvectors. Let's call them n. Okay. Now, what we can do is we expand this in terms of these n's, and there will be some expansion coefficients, and those will be like psi, like that. We usually don't write this in a product here, we write it like this. If we are only talking about one wave function, then we can use a simple number C or A or B or D. If we are talking about multiple states at the same time, then we maybe need to relate this psi over here. Then we may call it like psi n, and for another phi n, or if it's psi 1, psi 2, then that index should be here as well, but we don't need to do that. So we use just one symbol because usually we talk about only one vectors. So let's write this where. So this is projection of this operator onto this basis state, and these basis state by definition are eigenstates of this operator that we like to measure. So now this postulate says that we are going to get some eigenvalue. The probability for that eigenvalue is this. If we write it like this, then it's basically Cn mod square. So you can call it Born rule, but let's not do that. So it's basically this quantity. So once we have this, now we can compute probabilities for any observable for any state. So given a state and an observable and its eigenvalues and eigenvectors, we can form these inner products and compute these PNs. Okay, and but these are still probabilities. So if there are like 10 possibilities, some may be 0 if their Cn's are 0, some may be like around 0.2 or 0.5 something, but these are probabilities, so the sum will be equal to 1. Yeah. And that's why we usually use these states as normalized states. So if we normalize them, that length of this norm of this state is 1, then it satisfies this. Okay. So the measurement is going to get some nth eigenvalue, and probability for that is given by this. Now, if you prepare a system in state psi, suppose you are given that system is in state psi, You perform a measurement, you get, suppose A5, suppose you get A5, okay. So there is probability for different, but suppose you get A5. Then this postulate also says that as soon as you measure this and you get this, the system changes its state from this to this, okay. So system state collapses to this. That's why we usually call that whenever you perturb a system, quantum system, or you look at it, or you perform some measurement, the state of the system changes, okay. So that's a postulate here. So now collectively, when you perform a measurement, you are going to get some eigenvalue with some probability. That probability is given by this amplitude psi n, and soon after the measurement, just after the measurement makes this change. It collapses the state to this corresponding eigenstate. So if you get A5, state will be changed to 5th, okay. This 5th is eigenstate of this, and after that, now state can change due to some other reason, okay. So if a particle is moving, then its state is always changing because it's moving. So similar to that, for a quantum system, its dynamics will also be changing its states, evolving its states. So we will talk about that later today, but this is the action of a measurement, okay. Now if we have another system, similar system, identical system, prepared in the same state. So if you are given two systems, two isolated, they are not interacting with each other or anything, but just two copies of system in the same state. So first system is in state psi, another system is also in the state psi. So it has its own Hilbert space, but there is one-to-one correspondence, so we name them similarly. So it has its state psi, same eigenvalues for operator and everything. Now if you perform a measurement on one and we get A5, what would happen if we perform the same measurement on the second system? Can you guess? So it's like throwing two coins. So you throw one coin, you get head. You throw another coin.
So it's not guaranteed that on the other state you will get the same state after that.
Yes. So that's independent from this. So again, you have the same probability distribution, and probabilistically you get some state. It doesn't have to be the same. It can be any. Yes.
Are there cases where it's dependent?
No, these are isolated systems, copies of the same system.
Okay.
So no. So suppose you perform measurements on system 2 and its state collapses to state number 3, gives you A3, okay. Now what about these probabilities? These are theoretical numbers, okay, so you can compute them, but in experiments what happens? So experimentally you can also determine these probabilities by performing these measurements over a large number of times, yeah. So you make a statistically large ensemble of this system in this state, and you perform measurement, the same measurement on each copy, and you get some outcome. You keep track of how many times you get which eigenvalue, and after a large number of measurements, you can use that data to compute these probabilities. So these probabilities will be basically normalized frequencies of those outcomes. So this theoretical expression, it corresponds to that experimental probability distribution. Okay. So now if things happen like this, so there is a probability distribution, suppose there are like 10 states, and you have a probability distribution for different for these states, then what happens? Suppose you have probabilities. For 1 you have this, for 2 you have this, for 3 you have this, for 4 you have this. Suppose these are the probabilities and they sum up to 1, so I'm not labeling this scale. Then it means that whenever you measure, there is a wide range of values that you can get. Okay, so experimentally such measurements will not give you a single number. They'll give you a full distribution, and then you can do whatever you can do with the distribution. If it's a localized distribution, you can talk about its width and moments, etc. Yeah, but there is a special case. What if there is only one state that has unit probability and the rest of the states have zero probability? How can we have that? Well, that's easy actually. So if this state is an eigenstate of our operator that we are going to measure, then it will be one of these n's, and this will become a delta function, and for that given particular state it will be 1, and for others it will be 0. Then you will get that state and that corresponding eigenvalues with unit probability. That would mean that if you have statistically large ensemble of such systems in such states and you perform your measurement, you are certain that you will get that. So experimentally you will always get the same thing. You will always get the same eigenvalue. Suppose it's A3. If this is this, then you will always get A3 with probability equal to 1 and nothing else. So here we are not talking about experimental errors and stuff like that that are related to measurement. I mean, how accurate you can measure, how good your operators is and stuff like that. We are only talking about the limitations of quantum mechanics that it imposes onto the measurement of any observable. So if your state is an eigenstate of the operator that you like to measure, then you always get this. That means its probability will be 1 and 0. Okay, so this is 1. You are certain that this system has this value for this observable, and it's definitely that value. Okay, so in such cases what we can do is we can say that the system is in that eigenstate, and it has, this state has a definite value for that number. Okay, so it's certain, it's definitely that value. Yeah.
Is there any physical difference between the original state and, like, in the case where there's only one of the eigenstates has like unit probability, is there any like physical difference between the original state and just that eigenstate?
So
like when you measure
What you mean by original state? Psi?
Like psi,
Yeah.
psi. Is there any difference between psi and 3?
Psi and 3, there doesn't have to be any difference, but you can always multiply it with a number. But if you multiply with a number like 2 or 3, then its norm will be different, but it doesn't matter actually. But this formula will change slightly. You will have to divide it by all, sum over all, okay, to make it probability. Otherwise, you can multiply a phase. So it's like a complex exponential I theta for any theta. So that's a phase, global phase. So you can multiply that phase with this. It doesn't change the outcomes. Yeah.
So, how did you prepare a system that was definitely in just the state 3? And if it was definitely in the state 3, then after measurement,
Okay.
based on the probability, it should be in the state 3.
Yes. So it's basically an experimental thing, but it can be very easy in certain cases and can be very difficult in certain cases. For example, it's very easy to prepare a system in the lower energy state because systems naturally go to lower state. So if you have an atom, it's very easy to prepare it in its ground state. It's not an isolated system, it interacts with its environment, but it loses its energy if it has any, and even in thermal equilibrium, it will be in lower energy state with probability almost 1. But if you lower its temperature further close to absolute 0, for example, and it has other energy states very high up, then its probability will be practically 1 for its ground state. So these kind of states, they are very easy to prepare. You don't have to do anything. Yeah, just lower the temperature and system will go to its lower energy state. So you need to have a gap basically between lower energy state and higher energy states. So that's the easy thing. But in other cases, if you want to suppose prepare your system in first excited state, then you have to do something to it. So it's not that easy to lower its temperature. So then you have to lower its temperature so that it's 0. Then maybe you couple it with a laser, and laser give it that system some energy. Suppose it's an atom, then it couples with electromagnetic field, so it couples with laser, and it absorbs photons and goes to higher energy states. So if you have an ensemble, a gas of atoms, then shining laser on that, laser of right frequency, right energy, can put it to its first excited state. But then again, it's a practical task, a challenge to control the time for your laser. So if you keep your laser on, then it will go from here to there and then come back. Okay, even if it's the same frequency, it will oscillate between these two. I'll talk about such oscillations, depends on the time. And if you apply the laser for a right duration, then it will take your ground state population to its excited state, and then you switch off the laser, and then it stays there unless it is coupled to environment and loses its energy. It stays there for some time.
So back to his question, if you have a system in an excited state and you perform a measurement on it, would you get the state 3 after it?
Yeah, if it's in the 3 state, then of course you will get 3 state. The measurement that will tell you that it's in the 3 state will again be some maybe laser, probe laser. So you see, okay, you perturb it, or maybe just leave it and it naturally emits in the electromagnetic, there is electromagnetic field all around us, so it can emit a photon, say. So you detect that photon and you see, okay, this photon has this much energy, and you know its spectrum, and then you can tell, okay, it was in that state. So there are multiple things that you need to consider to be sure that what your measurement means and etc. But again, it's a practical challenge. For theory, it's very simple just to say that, okay, somebody prepares it in this state, and if we do this, this is what happens. Okay. Okay.
Explain his
Yeah.
point with the different example?
Yeah,
By
sure.
your permission?
Yeah, sure.
So the usual example that is used is the Stern-Gerlach experiment.
Yeah.
So that so you have an electron gun that shoots electrons, and electrons can have only two directions of spin. They can point along or opposite any chosen direction. Okay, so what you do is you pass it through a non-homogeneous magnetic field, and you will see an electron go either up or down. So before, so let's look at before and after. So what this over here, this apparatus actually acts as an evolution operator, e to the I h t. The initial state here, so psi initial I was some mixture of an up state and a down state. You don't know the coefficients C1 and C2, so you just write this, and that is the initial state. Afterwards, what happens is that psi final is then e to the IHT divided by h bar, the evolution operator acting on this initial. Now, if you take an electron, an electron could go up, or it could go down. It'll go up with probability C1 squared, and it'll go down with probability C2 squared. And then it will be in a definite state. Then it will not be in a superposition, it will be either up or it will be down, and the probability of finding it up is this, the probability of finding it down is this. Then you can keep putting more Stern-Gerlachs, and all those Stern-Gerlachs will measure it as up, up, up. So then it will be in a pure state. Here it is in a mixed state, and that is really the Copenhagen interpretation of quantum mechanics. So, but what you said was fine, that you cool something down, and then you can hit. Then it is certainly in the ground state. True. You can hit it with lasers, but this is the simplest way of looking at it. This is the way that Bohr looked.
Okay, thanks. Okay, so time is up. Okay, so next time we will talk about time evolution and dynamics of a qubit or spin half. Yeah, thank you.